Okay, so I suppose I'll start. I welcome the viewers to this problem solving and live interaction session for the subject Strength of Materials offered by Professor K. Ramesh on the SWAYAM portal. So today we will be discussing the contents of week 9, which has to do with the shear stresses and bending stresses. Yes, please. Just a moment, I'll come to that. So before we begin, what is the doubt in the previous assignment? May I know? If you can unmute and ask, that is also fine. Related to hacksaw, okay. Please discuss that. All right. Okay. So I'll discuss that and go about. I'll just briefly give the idea about how it was to be solved, and then we can go about doing the solving questions for the present week. Yeah. All right. Okay. So for those who are seeing this for the first time, I'll just briefly introduce myself. My name is Ganesh Amaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras, and I'm pursuing PhD under the guidance of Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So for all the previous videos, you can either log into SWAYAM portal. On the left side, there'll be a link to live sessions where you can find the previous 8 videos, or you can also scan this QR code on the bottom left of the screen, which will take you to the channel where they have been uploaded. Firstly, I tender my apology for week 8 because I found that after 40 minutes or so, the audio got cut. It did not get recorded. And this I noticed only at a later stage when I was rendering it. So I could not retrieve it. And it was too much for me to, solve again and do it. I could not find the time. So I tender my apology. And I'll make up for it in the future sessions if there are any doubts, as one person has asked here. So I'll discuss those, and I hope you can bear with that. So before we begin today's session, there is a question in the assignment, so which has to do with a hacksaw. So briefly, I'll just give a brief on what it entails. So we had a hacksaw like that. All right. So this is the hacksaw frame, and let this be the hacksaw blade. And I'll just put it in some different color like that. Okay, and then we have the handle over here, so on and so forth. And if we were to cut the cross section here, we will see that it was some U-shaped something, I think. So if I'm not mistaken, it was something like this. Just a moment. Something like that, I suppose. So this was the cross section. So the question says that the tension in this blade it is tightened. We have screws here where the hacksaw blade is put, and it is tightened. So it says that the tension in the blade is so much, some quantity. So, and we have been asked the bending stress and so on. So what I'll do first is, let me isolate the two things. I'll take the blade over here and let me isolate the frame like this. Fine. And I'll draw the free body diagram. So let me draw the free body diagram here. So this blade is under tension is what it is said. So we have tension here. So now we know that once there is tension here, the Newton's third law pair that needs to be applied on the blade would be in the opposite direction. Right. So on this end, I will just rotate this and I will apply it here. So far so good. So now that we have applied that tension in the blade to the frame, now it is just a question of resolving this. So we have taken a section here. presently. So if we were to take if you can see, if I were to resolve these forces at these points, so this will create a force and a couple like this. So this will create a force and a couple like that. Right. So this section essentially is subjected to a bending moment and an axial compression. I hope you are able to see that. So this can be equivalently represented as, if I remove this, I put it here. So this will be accompanied by a couple like that. And if I were to apply it here, I'll just remove the handle for a while. I'll put it here. So it will get subjected to a couple like this. Right. So now what has been asked is, so you consider this as a member which is subjected to axial compression as well as bending. What is the magnitude of this bending moment? We know what is the axial tension. We know this distance. So we know the moment, what is acting there. We know the axial tension, hence we know the compression in that section. So this is the cross section of the hacksaw over there, which is going to take that bending and axial compression. How do we calculate axial compressive stress? It is just force by this area of this. And as for bending stress, we discussed that once you are given a section, you have to arrive at the neutral axis first. So the centroid will be somewhere over here. This is a homogeneous section made of some steel or something like that. So the centroid of this will be somewhere around here, which will be the neutral axis, right? So this is the neutral axis, let us say. This you have to arrive at. And then this portion is subjected to compression or tension depending on the nature of the bending moment. And this will be, the bottom portion will be subjected to an opposite nature of stress. So the sum total of this, whether it creates yielding or not, is what is asked. Now, what is the doubt here? Is it clear, Miss Monty? Or anything specific that came about? Okay. Is it clear now, or are there still any lingering doubts? If they are there, please, it's clear. Okay. All right. Okay. So let us proceed with today's session and look at the first question. For a beam subjected to 3-point bending, I'll take a beam again, and let me apply a load like this. Let this be simply supported like that. The value of shear stress at the top and bottommost fibers at the beam at a distance L by 3 from the simply supported beam of length L. So this is given to be L. I have the load applied over here. Let this be some P. Now from the free end, I am told to take a section at L by 3, which comes somewhere around here. So I'll take a section like that. Let me call that section some MM. All right. So now at that section, I have to, I'll initially let me assume what the cross section is like. Let me take it to be a rectangle. Let the section, when we cut this at MM and view it like this, we will see, let us say we see this rectangle. This is section MM. Section MM. So what is being asked is, for a rectangular section, we know that the neutral axis, this is Y, this is Z, and along the length of the member, it is X. This is globally the coordinate system we are adopting for the origin. So for the rectangular section subjected to only bending, we know that our centroid, the neutral axis will sit at the centroid of the section. So I have put it at the middle of the section. Now what is asked is, what is the shear stress at the topmost and bottommost fiber of the beam? So what is the shear stress here and what is the shear stress here is what is asked. Now we are proceeding with the assumption where there are certain assumptions we are making here, which is we are applying the flexure formula, which is what is used towards deriving the shear formula, to a beam which is not subjected to pure bending. So as we discussed in the previous section also, our flexure formula is applicable only for cases of pure bending. It is exact for the case of pure bending where the deflected shape is a circular arc. In all other cases where there is non-zero shear, it is an approximation. But for slender members, it is a approximation that does not lead to too much of error. So that is why we go about solving these also. So clearly when we draw the shear force diagram for this, it will be like this. So any section of the beam is, there is no section of the beam that is free of shear. But we are taking section sufficiently far away from the loading point and we are carrying out an engineering analysis for the same. So we are applying the flexure formula here. Now, what is said is at these 2 points, what is the shear stress is what is asked. We can see that these are free surfaces. Regardless of whether flexure formula is valid here or not, if we were to revisit our discussion of a free surface, we can make out that these two are free surfaces. So at a free surface, let this be the let I take a point here and I blow it up to get the uh, for me to get the stress element. So here I know this will be subjected to, rather this will be subjected to compression first. So this is sigma x. This is subjected to compression because of the bending. On the top face is what is asked. On the top face there is no, it's a free surface, so there is no normal stress or shear stress. And by virtue of this being a free surface, we don't have shear this way because shear cannot cross a free boundary. As a consequence of that, we don't have shear stresses here. So the shear stress of the bottom and top fiber, bottom and topmost fiber are 0 in this case. So this is what I have blown up, and I have said that this is a free surface. So this is 0. However, nothing can be said as we come down into the section. This is for the top and bottommost fiber alone. As we come down somewhere in the middle, there has to be some value of shear because this is transmitting some shear force. And that variation, we in the lecture also it is derived from our shear formula, that is VQ by IB. I'll discuss that in the problems to come. From that, we find out that for particular shapes, they peak at the neutral axis, and the shear stress has a non-linear variation, which we will discuss in the questions to come. So I hope this is clear. And I am again, time and again, I'm ensuring that my audio doesn't get cut because as it happened in the previous session, the audio got cut after 40 minutes or so, and I was not able to retrieve it. So in case you also notice any anomaly, please do bring it to my attention. All right. So let us look at the second question. The variation of shear stress over the depth of the beam away from the loading points having a rectangular cross section is linear, parabolic, hyperbolic, or some random variation is what is asked. So basically we have a beam like this, and I take a section. Let this be the beam. For simplicity, I'm taking it as 3-point bend beam. It can be anything as such. And let me take a section here. At this section, the cross section of the beam is like that, a rectangle. Fine. So let this be B. Yeah, let this be B, and let this be, let me call this 2H. In fact, from our knowledge, we know that we are applying the engineering analysis here for the flexure formula, and we are taking this to be in case of pure bending. So our neutral axis passes through the centroid of the homogeneous section. So this is a homogeneous section. This is made of one material. So the centroid of this section is the place through which the neutral axis will pass. So let me draw the axes first. This is y, this is z, and this is x. For beam analysis, this is standard x. So when we look at the cross section, we can clearly see that x is actually pointing out of the screen. That is why x cross y becomes z with the right hand rule. So I suppose that is clear. So now that I have the neutral axis here, let me break this dimension here and let me call this h, and this also let this be h. Let the depth of the beam be 2h. Let the depth of the depth of the beam be 2h. The width be uh, b, and the length be l, which need not be marked presently. Now that we have understood this, let me move this out and place it here. That's fine. Let me take a section like that. I'll just keep the origin here, and let me make this smaller. Let me put this here. That's fine. So for this section, there will be some shear force, shear stress that gets induced at this interface between the layers. So what is that shear stress? So at this section, the shear stress tau x y. So the tau xy is given by V q by Izz into B, where V is the shear force that is acting on that section. Now I have taken the section at this point. Let us say I take the section here or here. Because of the problem, we will have a constant shear force here. However, if we were to take some other kind of loading, naturally the shear force at that section will depend on the kind of loading, which we can clearly read from our shear force diagram. So this is to be read from our shear force diagram, which is clear. Izz is what resists the bending in this case. This is Z. So the moment of inertia about this axis is what resists the bending here, which is what shows up at the denominator. B is our width of the beam at that cross section. If there is a variable cross section, naturally B also will be a function of x. Since we are taking a rectangular cross section for this case, B is constant. So these three terms are clearly defined. Now what is Q? Q is the first moment of this area. First moment of this area about the neutral axis. That is what is Q. Now let this be at a distance. Let me draw a line here. Let this distance be some y. At a depth of y, or at a height of y, howsoever you see it, from the neutral axis, I have cut a section, and my idea is to derive what is the shear stress at this generic section using this. So V, I, ZZ and B I know. So what is Q? Q is the area of this, moment of area of this about the neutral axis. If this is h and this is, if this distance is h and this is y, I can clearly see this is h minus y. So let me go ahead and populate this. I have this here. So I have V at that section by, what is I for this IZZ? Is nothing but B d cube by 12. Since the depth I have assumed it to be 2h, I just have to substitute 2h there. So when I substitute this, this will come out to be 12 V by B h cube, and I'll have an 8, and I have another B here, so it will become B squared into Q. I suppose there is no confusion on how this figure has come about. I've just substituted IZZ. Now, at this section, let me substitute for Q. Q is the first moment of area. So I'll just have this figure as it is, 8b square h cubed into what is the area here? This is again a smaller rectangle of width b and depth h minus y. So its depth is b into h minus y. And the moment of this area about the neutral axis, meaning the centroid of this, the distance of the centroid of this from the neutral axis needs to be multiplied, which is nothing but this by 2 plus y. I suppose there is no confusion in seeing that, into y plus h minus y by 2. This is the area and this is the distance of the centroid of that area from the neutral axis. So this entire thing is what is Q for this section. If I were to change the section somewhere, only my y changes. So I have actually written the formula in a very generic fashion where I can see what is the variation about y. I hope that is clear. So let me just simplify this. Okay, so this will become 2y plus h by 2 if I take the entire thing divided by 2. So this makes it 12v by 8b squared h cube into b into h minus y into, I can see this is h plus y by 2. Yeah, I suppose this is okay. So this will give me 12v by 16b squared h cube into b into h squared minus y squared, a plus b into a minus b. So this is my shear stress variation across the depth. You just keep an eye out for the exponent in case there are any issues there. All right. So what does this tell us? This tells us that this shear stress variation is parabolic in y. When that is, as I change y, I should get a parabolic variation. Now let me see if this is consistent with our knowledge of free surface. So at y equal to h, above this, when I go h distance, I reach the free surface. This goes to 0 because this also becomes h. So tau xy is 0 at y equal to minus h. Because the axis is this way, if I have to reach the bottom free surface, I have to take y equal to minus h. In such a case, this will become, again, this will become 0, tau xy equal to 0. At the neutral axis, at y equal to 0, which is at the neutral axis, this shows the maximum value, which comes out to be what? Tau xy reaches tau xy max 12v by 16 b squared h cube into b h squared, which gives me 12v by 12v bh. So bh gets cancelled. 16 bh. There seems to be something. Yeah, okay. So if I were to take half of this, see the area, The total area of this rectangle is 2BH. Fine. So if I were to rephrase this as in terms of 2BH, this will be 8 into 2BH. So this comes out to be 12B by 8 into 2BH. I'll just recast that in another form. So this is actually 12 by 8, which is 3 by 2. 3 by 2 V by area. Because that 3 by 2 was not coming, which is why I was looking for what the problem was. As such, there is no problem. So this tells us something. In general, we have seen what is stress. It is just force by area. When the stress is normal in nature, we divide it by that cross-sectional area and we get the normal stress. In a similar way, when we have shear force and an area, we divide these two and get the shear stress. We divide the shear force by the cross-sectional area and we generally get shear stress, which is what is this V by area. But this analysis tells us that the average shear stress which we take as V by area at the neutral axis, this will be the stress, actual stress will be 1.5 times of the average stress. Whereas at the top and bottom fibers, there will be no stress. So instead of a rectangle, we actually have a parabola as the variation. So I suppose you are able to appreciate that. This has many names. Some books refer to this as shape factor. So this is actually a function of the geometry. So I took a rectangular cross section, which is why that shape factor came out to be 1.5. That factor is nothing but it tells us how much we need to scale the shear stress, scale the average shear stress in order to arrive at the maximum shear stress that is getting induced at the neutral axis. That is what that is. So for circle, it might be something different. I don't remember the value. You can easily derive that in a similar vein and see. So the sum and substance of this discussion is the variation of the shear stress over the depth of the beam for a rectangular cross section is parabolic. So I hope you're able to appreciate that. Are there any questions at this point? Something that is not clear, or am I going too fast or too slow? Something. If there is any feedback that you want to give, please feel free to unmute and interrupt me. I can perhaps make some amends. All right. So if this is clear, let us move on to the next question and see. The stress tensor at a point P. So we have a cantilever beam. I need not draw it again. So we have the axis x, y. So naturally, when I draw the cross section, this will be y and this will be z. I suppose that is clear. So we have a point which is taken somewhat beneath the top surface. It is not exactly at the free surface. It is somewhat beneath into the depth of the beam. Based on the strength of material solution, the stress tensor here can be represented as which of the following. Now, what does this mean? What does this phrase mean? Based on strength of material solution. This basically implies that we are doing an engineering analysis. This means that we had the flexure formula is being applied to cases with non-zero shear. I know for this beam, what is the shear force diagram? It's a rectangle, but the bending moment diagram is a triangle like that. Howsoever you want to interpret based on the sign convention. But there is non-zero shear throughout the beam. It is not in a pure bending. But the flexure formula is derived only for pure bending. So we are extending that to apply as an approximation to this problem, which is why it says strength of material solution. If we have to arrive at the exact solution for this, then we should also consider the depth of the beam, which is what we do in higher level courses like theory of elasticity. That is what we do and actually find out how much the difference is based on a simple engineering analysis and an exact analysis. How does the how much is the error we calculate, and based on those calculations only we say that for a slender member this approximation is not worrisome, it is acceptable. All right. So at this point, we have been asked to calculate the populate the stress tensor. So what I'll do, let me take this. I'll put it here. Let me assume a sign convention like that. So I have exposed the negative surface. So let this be my bending moment, and this, let me give this some value. Let this be the load be L. So this distance is nothing but some x. So I have a bending moment which is Lx over there, which is negative. So at x equal to 0, bending moment is 0. At x equal to L, it is L into, oh, but I should have, it's a poor choice of this thing. All right. So load is also L and length is also L. I suppose you can bear with that. So we know that sigma x from our flexure formula. We know that mb by izz is minus sigma x by y equal to E by R or rho or whatever. It is basically the radius of curvature of the circular arc. Now from here, I can see that my bending stress is nothing but this. So this is my bending stress. So Y, it is not taken at the centroid of the section, but it is taken at some distance. We can clearly see it is not at the center of the beam, but it is somewhat away. So Y is non-zero. IZZ is anyway non-zero, and bending moment we just saw it is at a section that is away from the free end. The bending moment is also non-zero. Hence, sigma xx definitely exists there. So we have to look out for options that definitely have sigma xx. These two don't have. So these two clearly cannot be our stress tensor at point P. We can see that these two are still viable options. Now, in addition to at point P, if I were to draw the stress element like that, what I see is I have sigma xx like this. There is no sigma y. There is nothing applied along the vertical direction. There is only shear that gets transmitted from one section to the other. So shear is getting applied this way. So at this point, there is a non-zero shear because this is not at the top. We just saw at the top it would have been 0 by virtue of being a free surface. It is not at the top. It is not at the neutral axis also that my sigma xx goes to 0. It is somewhere midway. So both shear and the normal stress exist there, which is why this is the correct representation where there is these three are having non-zero values and my sigma yy is 0 at in that case. So are there any questions about what we discussed at this stage? Okay, so I take it is clear. All right, so I'll move on. What will be the shape of the isochromatic fringes for the case of a cantilever beam shown in the given figure is what is asked. Now let us revisit a bit on photoelasticity. This is the technique which gives sigma 1 minus sigma 2 contours in the form of some nf sigma by t. Basically, these are nothing but constants. So if I take f by t, f sigma by t to be unity, N basically N can be 1, 2, 3, and so on. Difference between engineering analysis and exact analysis. See, we have derived the flexure formula for the case of a purely bent beam. That is, for this case where this is MB, uh, MB by IZZ. If you revisit the definition, if you revisit the derivation of this flexure formula, we would have initially considered a beam like this, which is subjected to pure bending, which has no shear. And we have made no assumptions in the steps, and we have arrived at this. So this is actually an exact solution for this problem. Whereas when we have the case where I have a non-zero shear, let us say that this beam is also subjected to a shear force like this. I know that throughout there is shear force that is acting. So a beam like this, it will have a shear force diagram like this. Whereas a beam, this is just the shear force. There is no shear force. So when I extend the applicability of the formula by ignoring the shear, when I extend this to this case also, this is engineering analysis. So this is the exact analysis. This is engineering analysis. Yeah.
Sir, so basically in the assignment there were question that the flexure formula applied to this problem is engineering
Yeah.
analysis or not. Then there we had to see only that shear
Yes,
force
whether
is
the
zero or not.
section is subjected to pure bending or not. Whether it is pure bending or whether there is no shear force, it is one and the same. Different ways of saying the same thing. So that is what you're supposed to check. Okay, yeah. This
Okay,
is
sir.
asked in the interest that the learners know whether they are doing an exact analysis or not. Because we can easily apply flexure formula to many cases, but we should also be aware where we are making an approximation and where we aren't. That is the idea behind this question. Okay.
Okay, sir.
So photoelasticity gives sigma 1 minus sigma 2. Now, in the case of a, let me first take the case of pure bending. And let me conveniently take this over there. So here I know that again I'll just take the y there. So this is my sigma x. And sigma y is is 0. In the case of pure bending, I have no shear. That means if there is no shear, then VQ by ICZ, V is 0, so tau xy is also 0. If tau xy is 0, that makes these two principal stresses. So if when tau xy is 0, this becomes sigma 1 and this becomes sigma 2 when this is positive. If that is negative, it will just flip the signs. But regardless, we always take sigma 1 to be the algebraically greater one. So sigma 1 minus sigma 2 is essentially always positive. I hope you are able to appreciate that. In the case of pure bending, either one of these goes to 0 and the value always remains positive. So the value is invariably this, equal to nf sigma by t. So the only variable here is y, correct? So as from the centroid, as I move y either to the top or to the bottom, all I should see is just constant color change, which is what actually happens. So if we were to see in this case, for this case, if I actually see how the fringes are, which is shown in the lecture also, I'll see these are nothing but straight lines, which are equidistant from each other, of different colors. If they are equidistant, it implies that there is a linear variation along the depth. Now, with that background, if you were to revisit this question, what this says is, in a cantilever beam, how will the isochromatics look? We know that in a cantilever beam, shear is non-zero. And this is from the perspective of an experiment. So in reality, what happens is what is asked. If it is shown in the lecture also, when we see a cantilever beam in a polariscope and load it, we will see that here the lines will be like this. So we will be seeing variations like this. Why this variation comes, why it is not a straight line, is because of the presence of tau xy. So at this point, at any point, when I draw the stress element, my sigma x alone doesn't exist. There is some tau. So I have to rotate it in such a way that I get uh, the principal stress is at some other angle. So which is why we basically see curvature, curved lines as our fringes. If we were to load it uh, in a pure bending setting, we will see that these become straight. So I hope that is clear. So these are curved lines. Are there any questions about this? Okay, if we were to revisit the other answers, let us just take a guess about how that would be. Straight lines parallel to the x-axis from the free end to the fixed end. From the free end to the fixed end, if these are straight lines parallel to the x-axis, that means it is a misnomer how we are naming it. By some means, this is subjected to pure bending only. About this axis, straight lines parallel to y-axis. If it was like this, then we are looking at a portion of a beam in a flipped manner. However, we can interpret that, actually speaking. Curved lines is what actually we will see here. Constant color throughout the domain. Constant color means others are constant, that this difference is constant. We already saw in the case of uniaxial tension, sigma 2 goes to 0. Sigma 1 is constant away from the loading points. So once that is constant, there is no variation about the spatial coordinate, and hence we will see a uniform color. If we increase the load, it will be a uniform color of some other RGB value. It will be some other uniform color. I suppose you are able to appreciate that. Okay, so all right, so let us look at this question. Identify the correct variation of shear stress along the depth of the I section as shown below in the figure for the load applied in the y direction. So the load is applied like that. And this is the cross section. Of course, the beam is like this. At some section, when we are looking, we see an I section like this. And what is asked is, how does the shear stress variation take place? So what I'll do is, let me just take the example of the same rectangle and then build upon that in order to come to the I section. So let this be the rectangle. So for this rectangle, I know at this cut, the shear stress tau xy is Vq by Izz into B, which came out to be, we had derived that earlier. I'll just use that same expression. Yeah, here. It'll just be this. In other words, what are constant here? V is constant. B, H, all these are constants. Only Y is having a variation. As we vary it, the shear stress is varying parabolically. So by virtue of this discussion only, we said that our variation is like this, which becomes 0 at the top and bottom, and at the centroid of the cross section or the neutral axis, it peaks to 1.5 times its value for a rectangular section. Fine. Now, if I extend the same logic to an I section, how is an I section different? So essentially, this is my I section. If I just remove this out, so this is my I section. So as long as my section is being cut in the flange, these two are called flanges, and this is called the web. Basically, flange takes the bending and web takes the shear. Is the basic design philosophy of an I section. So as long as my section that is being cut is within the flange, my variation remains unaffected, as we can see here. If I were to draw a line like this, till this point there is no change. That is, the graph till here still remains the same. There is no problem. Now when I come to this section, there is one more variable that jumps into our formula. We know tau xy is this, but at the junction, our B also can be either the flange width or the web width. So B of the flange, either we can take, or B of the web. There are two possibilities for this, which is why it shows a jump. That is all the difference is. So what will happen is, I'll duplicate this. So it will just show a jump. Why? Because if B suddenly becomes less, B squared is lesser than that. If B becomes half, B squared is 0.25. So this eventually shoots up higher than 1. The ratio will become higher than 1, which is why I have moved this to the right. So it will show a positive jump. It will increase its value, something like that. And I can remove the portions which are not relevant here. So I'll just delete this out. And inside this, I'll just remove this out. So I can see this is the jump that I'm talking about. So basically, this is my variation. I have drawn the parabola in such a way that the curvature is a little bit flat, which is why this appears to be a straight line. I hope while following this discussion, you can appreciate that this is actually a second degree curve. So please don't consider it to be a straight line by how it is looking. This does have a curvature. All right. So this is the difference in the case of a I section as opposed to a rectangular section. Now, once I go into my web, no matter where I take, again B becomes constant, which is equal to the width of the web. So as long as I'm in the web, again it is the same parabolic variation but with a higher value. At this junction, again it will show a drop and it will still continue to be a second degree curve. I'll better write it as second degree, in case someone were to misunderstand that as a linear variation. It is a second order variation. All right, so we can see from here that this shows, and then this shows a jump, and then again it is a parabola. It is nothing but a parabola which has been pulled to the right by virtue of the jump in the width here. That is all there is. So A is my correct option. I hope that is clear. If there are any questions at this point, please feel free to ask. Okay, in any case, I will proceed then. Should there be any questions, please do ask. And this is also second degree variation. Okay. Shear center of a beam is the point on a beam where the axial force is maximum, where the shear force is maximum, bending moment is maximum, or the point where when the applied load produces no twisting. So it is discussed in the lecture also, basically for open sections when we take open sections, because of the asymmetry, what happens is, unless, so this has a variation like this. Along the depth, it will still be parabolic variation. But we can see that when I take, let the coordinate start from here. When I take moment of this area and the moment of this area, as I proceed in the flange, I can see that I will only have a linear variation in y, because it will just be y to the power 1, because y is essentially same for all these sections. So we will have a variation, shear variation like this, and there will be a parabola. Essentially what happens is, this is transmitting one shear force in the form of shear stress. So this shear stress, if it were to form a couple, this has to be counteracted by the applied load. Otherwise, this will twist. So if I have a couple that is getting formed by this, which I need to nullify, I need to apply a couple this way. So about the centroid, if I want to apply a couple this way and my load is pointing like that, let the load be pointing downwards like this. This is my shear force. The the couple that is getting generated by virtue of the shear stress is this. So we need something to nullify that is like that. So if my shear force is fixed, about which point should I apply such that it creates a couple of equal and opposite magnitude, equal magnitude and opposite in nature. So I can see if I were to apply to the right of the centroid, it will still create the same nature of the couple. So if I were to apply it here at some considerable distance, so this V into that distance creates a couple that nullifies the twisting effect. This is the essence behind the shear center. So this point is what we refer to as the shear center, and this distance we can calculate based on, we know this couple, we know the shear force. So by balancing the moment about the x-axis, because x is pointing out of the screen and this is the cross section we are seeing, by balancing the moment about the x-axis, we'll be able to find this distance. And this is recommended when we use open sections for design. We generally ensure that these are symmetric. If they don't happen to be symmetric, we will ensure that the shear force passes through the shear center. Or if it does twist, we will have to design for that twist. Either one of the two, whichever is economical, and so on and so forth. So this is the point on the beam where the load produces no twisting, where the applied load produces no twisting. So I hope that is clear. Okay, so let us look at this question. The typical variation of different stress components, these are not drawn to scale, it is said upfront, because it is discussed in the lecture also. Generally, books, they show the bending stress like this and the shear stress like this, which gives a notion that they are nearly of equal magnitudes, whereas actually if we were to work out the values for a slender beam, we will see that if we were to draw it to the scale, this will be very, very less in magnitude. It will be a very flat parabola, which means the shear stress is orders of magnitude less than, at least one order of magnitude less than our bending stress in slender sections in general. Typical variation of different stress components over the depth of the beam having a rectangular cross section when loaded along the y direction is shown. Match the figure with the correct caption, enter the corresponding alphabet, so on and so forth. So what we are having is, we have a beam like that. Let us take that to be slender. And it is loaded in some form. So let this be W kilonewton per meter. Let this be length L. Now at one typical section, this is what I see. This is the section at that point. This is X. I know by virtue of this being a rectangular section and my engineering analysis, I know that a linear variation implies this is the bending stress, which is sigma x. So sigma x is A. Other than this, I see there is a parabola. There is some second, it has a lot of inflections, and I have a variation like this. So this I know to be the shear over the depth for the rectangle, where we just saw that this value will be 1.5 times the average shear stress. In this case, when we consider the corrections, that is the theory of elasticity solution that has come in here, the term, when we apply only flexure formula to this case, we note that our variation of the normal stress is linear, whereas if we were to account for the presence of shear also, which it is not done explicitly here, it is a subject matter of a higher level course called theory of elasticity or advanced mechanics of solids or whatever. In that case, we will be able to see that along the depth we will have some variation in sigma x uh, by virtue of the presence of shear. So this is the correction to that actually. So C is the correction to that. And throughout the discussion, we have only focused on 3-point bend case, where if I were to take a section, the top surface is free, the bottom surface is free. So there was no traction at the top or bottom surfaces. Whereas in this case, if I take a section here and I see on the top face, I have the load applied like this. On the bottom face, it is indeed a free surface. So we can see that there is a compressive stress that is applied on the top, which shows a variation and goes to zero at the bottom by virtue of that being a free surface. So this is actually the variation of sigma y in a case which is loaded with a uniformly distributed load, sigma y. But if this were to be drawn to scale, we will see that this will peak. This will be visible. If this is drawn such that this is visible, others are barely second order effects, which will be very less. But in order to do an exact analysis, we might have to include that in our uh, solution. Otherwise, we can disregard them, keeping in mind that we are doing an approximation and account for that in our factor of safety and so on. So I hope that is clear. All right. So this question says, for which of the following cases plane sections remain plane before and after loading? An axial tension of a rod of hexagonal cross section. We know that in the case of axial stress is P by A. Sufficiently away from the loading points, it is simply P by A. It does not depend on what the area is. So no matter what the cross section is, even if it is shaped like a potato and it is stretched lengthwise and we pull it, invariably plane sections will remain plane. So there is no dependence on the area. So this is true. Twisting of a shaft having a rectangular cross section. Now this is also shown in the lecture. For those who have not seen this, can revisit that. There is a very soft material which is bent, and even in it is part of one of the assignments where we see that a warping clearly takes place. So when we have a straight line like that, when this is twisted, we can see that this line basically shows a curvature like this, which means there is some out of plane distortion that is happening. So plane sections don't remain plane. in rectangular sections, but this is true for circular sections by arguments of symmetry also, which is the subject matter of one of the lectures at the starting of torsion, where we have done a thought experiments about why plane section has to remain plane in the case of a twisting of a prismatic circular shaft away from the loading points. So this is true. Bending of a cantilever beam with the load at the free end, we just saw in this case that here we are actually going for an engineering analysis. Since shear is non-zero here, in reality, what will happen is the section will be warping like that as we go on. It won't be straight in the bent beam. So plane sections do not remain plane in such cases, but within acceptable limits. So this is incorrect. A beam of rectangular cross section subjected to pure bending. This is the classic case where we have seen umpteen number of times that plane sections remain plane. Not only plane after bending, they also remain normal to the neutral axis post bending. So this is true. All right. So yeah, so enough of theory. So let us do some numerical problems now. So this says an aluminium beam having a box cross section. So box, actually speaking, it is just a rectangle. That is what is being referred to as a box here, not to be construed with hollow this thing. An aluminium beam having a box cross section is strengthened by riveting a steel plate of thickness 20 mm. So we have taken a steel plate of 20 mm thickness and we have riveted it with the bottom of the aluminium beam. So the rivets are not shown here for clarity. The Young's moduli of aluminium and steel are 70 and 210 GPa respectively. So we have EAL as 70 GPa and we have E steel as 210 GPa. Okay. So the beam is subjected to a bending moment of plus 50 kilonewton meter. So MB is given to be plus 50 kilonewton meter. So this is where we are coming into a section which is not homogeneous. Now we can see that clearly there are two different materials. So this is not a homogeneous section. Now we will have to do some jugglery in order to apply our flexure formula in this case. Either we transform everything to a uniform one section and go about doing the analysis, or we take it piecemeal and integrate and so on. When we take it separately and integrate, the method is called the curvature approach. If we were to transform everything in terms of steel or everything in terms of aluminum, it is the transformed section approach. Both are essentially same in a way, but transform section happens to resonate more with people who can do it without much integration. So let us see how that is to be done. If the steel section is transformed to aluminum, determine the transformed moment of inertia and so on. So let me digress a bit here for the sake of discussion. So I have the section here. Fine. So if this was steel, if this was, the steel was also aluminum, essentially. If this plate was also aluminum, we will be having a uniform 300 mm deep aluminum beam, in which case our neutral axis would have been at the center of that 300. That is at 150 from the top, we would have had the neutral axis. But that is not the case here. We have a steel plate and we know that steel is stiffer than aluminum. So if it is stiffer than aluminum, what it will do is it will pull the neutral axis towards it. So if half depth is 150 mm of the beam, we can expect the neutral axis to be greater than 150 from the top fiber by virtue of steel being steel being stiffer than aluminum. So let us go about finding out where the neutral axis is. The first question is, where is the neutral axis? And why do I pose this question? What have I been asked? Transform section, determine the moment of inertia, and ultimately I have to determine the bending stress in steel and aluminum. So it waters down to my stress analysis only. And for stress analysis, presently at my disposal, I have only the flexure formula. For stress analysis, we have the flexure formula which says MB by, but this has been derived for a homogeneous section where Y is clearly defined. I'm sorry, just a moment. Here, Y is distance from the neutral axis of the cross section. So MB I know, IZZ I can calculate for this section, but even for that I need to first locate where the neutral axis is, because IZZ has to be about that neutral axis, and the coordinate Y, the distance Y which I take, its origin sits at the neutral axis. So which is why my first question, primary question, is where is the neutral axis that I need to find. Now if we were to revisit our derivation that is done in the lecture, for the case of a homogeneous beam, how did we find the neutral axis? Basically, in this, for this cross section, for a rectangular cross section, I have the variation of stress like this, let us say. So neutral, to locate the neutral axis, we used force equilibrium, sigma fx equal to 0. Since there is no external force applied, because the section is subjected only to bending, there is no axial force presently applied. In such a case, sigma fx on the right side, it will be 0. So what is sigma fx? I have sigma x dA. Integration of sigma x dA is 0. And what is sigma x? I know it is from here. If I were to take these two, this will come out to be sigma x will be minus y e by r. So if I substitute that here, I get minus y e by r dA. Integration over the section is equal to 0. If e and r are constants, I can take that out. What this gives me is integration of y dA equals 0. So this tells me that the neutral axis is at a point about which, if I were to take the moment of the entire cross section, it equates to 0, which is the very definition of a centroidal axis, which is why this was coming at the centroid of the cross section. This was the neutral axis, which is why this was coming at the centroid of the cross section. Now let us extend the same approach. So this is the case of a homogeneous beam. Now let us apply the same, extend the same approach to this composite beam. Here, let this be the neutral axis for the sake of discussion, I'll just erase this. Let me say that my neutral axis is over here. Let this be y and let this be z. Let that be the neutral axis. And let this distance to the neutral axis, let this be some yt. Y from the top, I'm just taking as a general this thing, I'm taking that to be yt. If that is the neutral axis, then what is this distance till this fiber? So this is nothing but if I go yt above and then I come 280 below, I will get to this point. So this is nothing but minus of 280 minus yt. Similarly, this distance up to here, it is minus of 300 minus yt. Is there any confusion about how these values have come? It is actually the coordinate of this point. If I have to write the coordinate of this point, this fiber with respect to the neutral axis, I have to go down. So that is why the minus comes in. And the entire distance is 280. The top is yt. So what is the remaining? It is 280 minus yt. That is how the coordinate of that point has come. Similarly, for the extreme fiber, it is total depth minus yt. And because it is it is towards the negative direction, I have put a minus. So this will be plus yt. So what I have done, I have just written the coordinates. I just written the y value at these three fibers. That is all I have done. Now let us equate the forces. So sigma fx equals 0. What will that give me? There is some stress in aluminium and then there is some stress in steel. I am going through a circuitous way of the curvature method, and eventually I will come at the transform section method in order for the viewers to appreciate that why transform section method better resonates, why we can avoid the integration and so on. But I want to show what is the similarity about why we scale things. So that will come out as a consequence of this analysis, which is why I'm going through this circuitous route. I request the viewers to please bear with that. So sigma fx equaling 0 gives me force in aluminium plus force in steel equals 0 because there is no axial force anyway. So force in aluminium is stress into area. So I just need to integrate the stress in aluminium over its area, and I need to integrate stress in steel over that respective area equaling 0. But I already know a value for my stress. But this I already know. When I take them individually, they are still homogeneous where I can apply this. So I will apply this piecemeal. So therefore, sigma x in aluminium can be written as minus of y into E of aluminium by R. Similarly, of steel, I just need to replace these with steel. Now one might ask, why are we considering a common radius of curvature? If it is not common, just if you were to imagine a section, beam section like this, if they do not have a common radius of curvature, one will have bent this way and the other would have bent in some other. So there will actually be debonding. But the question says that these are riveted together. Rivets are not shown, but these are riveted together, acting as a monolithic unit. That is why for the entire beam, irrespective of the material, the radius of curvature will still be the same. If the radius of curvature is not the same, then the bond here has broken. That is what it implies, which means it is no longer a strengthening uh, piece to the strengthening plate. The plate is no longer strengthening the beam. That is what it means. All right, so it is just a matter of substitution. So let me substitute that. So it is this into dA, and this I have to integrate over the area of aluminium. Similarly, I have this. This I have to integrate over steel, area of steel, and these two still come equal to 0. I shouldn't have. Yeah, very well. So I have got this equation, the solution of which will actually give me the neutral axis because I'm following the same approach. So let me take this and simplify this a bit. So E and R are constant, so I will take them outside. E and R, I'll take them outside here. Now R is common between the two, so I can just take it to the right and cancel it out. So R I can actually remove. If I multiply the entire equation by R, right side is 0, so it just disappears. So I have only this. There are two minuses, so if I were to multiply the entire equation with -1, that also disappears. This also disappears from the equation. So I am left with this simple equation. If I were to correctly integrate this, I will get the value of the neutral axis, which is yt from the top fiber, or howsoever you want to look at it. Because we have taken yt to be the variable, if I plug them in the integration correctly and I force the equation to be equal to 0, I will get a value of yt, which means I will get the location of the neutral axis from the top fiber. This is the entire activity that we are doing. And we will see how with the transform section method this becomes very easy. So let me divide the entire section by EAL. So I have divided the entire section. Now what does this tell us? That I have the area of aluminium integrated. I have YdA integrated over AL, and I have YdA integrated over, only that steel gets scaled by its corresponding stiffness. That is, EST is 210, EAL is 70 as given in the question. Where is that? These are given in the question. So actually we have to account for steel 3 times more. This is why we basically, in the transformed area method, we will scale the steel by 3 times its width. That is a consequence of this equation only. That is what I'm trying to say. So let me substitute the limits. I will take this figure from here. Or we can see it from here itself. For aluminium, it will go from this point to this point. From here to here, it will entirely cover aluminium. So I just need to appropriately put those limits. So this is nothing but integration of minus 280 minus yt till plus yt. Y dA. What is dA for a rectangle? For a rectangle, if I take a strip like this of depth dy and width b, so what is its area? B into dy, that is dA. So 1 minute, and seems to be some issue with the screen. Yeah. So this is B dy. This is the area of that strip into y plus 3, or rather, let me not say 3, let me call this m. As they famously call this is called the modular ratio. This is called the modular ratio, the ratio of the Young's moduli. So here it will be m into, and steel, we can clearly see that steel goes within these two limits. So that is what I need to substitute there. So let me go ahead and substitute. It goes from minus 300 minus yt to minus of 280 minus yt. Integration of again b dy, sorry, the same thing. This equals 0. So the solution of this is going to give us the neutral axis. So this will be, again, from this equation, I can take out b common and take it to the right side. It goes to 0. So b doesn't matter here actually. So if I were to integrate, this gives me y squared by 2 over the limits yt to this plus 3 by 2. I substituted for m equal to 3. So this is 3 by 2 y squared over the limits this equaling 0. So this gives us yt minus of 280 minus yt the whole square, entire thing by 2 plus 3 into 280 minus yt the whole square minus 300 minus yt the whole square. In fact, 2 is common, so I need not even take it, equaling 0. So I just need to open this up. I have substituted the limits. I need to open this up. Interested viewers can actually open this up and see what this comes out to. But I'll just use the calculator to do the integration quickly in the interest of time. Plus 3 into, this 3 is common, mind you. Yeah, so this is 280 minus x the whole square, 380 minus x the whole square equals 0. So this comes out, this gives me some quadratic equation, the root of which, one of the roots, viable roots will be 166.47 mm. So we have got an interesting result here. We have got yt, the distance yt as a solution of this as 166. Now let us reflect on this whether that makes sense. The entire depth of the beam is actually 300, but it is made of it is not a homogeneous material. If this was entirely aluminum or entirely steel, we would be having the neutral axis exactly at half of that 300, which is 150. But presently we have stiffened it with a steel plate at the bottom, which means the neutral axis will get pulled down. From the top, it would have been 150 if it was homogeneous, but presently it is 166. So this has been pulled down because of our steel plate. So this makes sense. So this is my neutral axis location. Now what I need to do, I have equated the forces. Now I also have to equate the moments, which I won't do completely because it will become very tedious. So I will quickly switch to our transformed section method and solve this question. But I just wanted to give a flavor of where things are coming from to put things in perspective. All right. So for the homogeneous section, now sigma, we have actually used sigma fx equal to 0 in statics, we have three equations, sigma fx equal to 0, sigma fy equal to 0, sigma m about z equal to 0. Actually, it will be about z. Now, sigma fx equal to 0, we just used. Sigma fy, there is no force in fy, or we would have used that to calculate the actual reaction of the beam. So that also we have employed. So sigma mz equaling 0, this gives me, there will be a bending moment like this. So this sigma mz, it will not be actually equal to 0 for this section, or rather, let me take that to be equal to 0. That will make more sense. So what this is the moment due to the stress and the bending moment should add up to 0 effectively for equilibrium to be maintained. That is the main uh, aspect here to be looked at. So at any distance y, I have sigma x pointing in this direction. So what is a moment? Moment is nothing but r cross f. So y crossed with sigma x what will give me my moment. So integration over the aluminum section of y crossed with sigma x dA. This is the force and this is the lever arm. So this gives me the moment due to the stress in aluminum plus, let me say aluminum, sigma x in steel dA. And we can see that y cross f is actually creating a clockwise moment, which in equilibrium should be negative. So I'm sorry. So this is minus, and then minus mb equals 0. So far, so good. So we have mb equals, I'll just take this to the other side. I have this quantity equal to mb. Now, if I were to do the cross product, before I do the cross product, let me substitute for sigma x al. I had the value of sigma x al and sigma as this, if we remember from the analysis. So I'll just copy this. I'll take this here and I'll substitute now. Substituting mb comes out to be, so there is a minus here and there is a minus here, both get cancelled out. So I have EAL by R integration over the area of aluminium y square dA plus E steel by R integration of y square dA over the area of steel. The first moment of area, we had seen that it was equating to 0, whereas here that is not the case. So what does this basically tell us? We know that this is nothing but the moment of inertia of the aluminum section about the neutral axis of the entire section, which we derived here to be 166 from the top fiber. So this is so MB is actually equal to EAL, IAL, where AL is for aluminum by R plus E steel, I steel by R, where IAL and IST are moments of inertia of sections and steel about the neutral axis. So this is nothing but MB is EAL, IAL plus EST, IST by a common radius of curvature, or this another way to write this is 1 by R which is the curvature, is nothing but mb by this quantity. So we have got something interesting here. In the case of a homogeneous beam, what was our curvature coming out to be? 1 by r was coming out to be mb by ei, because E and I was common. Whereas if we have two materials, it is just like a weighted product, sum of the weighted stiffness, weighted flexural rigidity, so to speak. So EAL into IAL plus EST into IST. If I can clearly see here that if I were to add one more plate here made of some brass, then I can, by doing this very activity, I can clearly see that my curvature will just be some E brass, a I brass. Only difference is I will have to recalculate my neutral axis again, as we did for sigma fx equal to 0. That I will have to do that activity again. So that is all there is. So now, where this becomes more messier is MB is given. EAL and EST we know. Now I have to calculate IAL and IST about the neutral axis of the actual section, which is 146, 166.47. So that is what we have to do. So let us go ahead and do that. So IAL, and I'll have to bring in the beam also. So let me just get it here. Copy. So for this beam, I know that the neutral axis is somewhere here. The neutral axis is somewhere over here, which is at a distance of YT, which is 166.47. So IAL will be the moment of inertia of this aluminum section about its centroid, plus I will apply the parallel axis theorem. So this is IAL self. This will be IAL self or about its own centroid plus A dy squared. So this is nothing but our parallel axis theorem. I hope everyone is comfortable with that. Same goes for steel. So I steel self plus A dy squared. So this is A aluminium, this is A steel. So let us quickly calculate this. So IAL is nothing but, I know this is 200 into 280 cubed by 12. That is about its own centroid. I have to account for the shift. 200 into plus 200 into 280 into what will be the shift? The actual center of this aluminium is 280 by 2 from the top, and the neutral axis is at 166. So it is 166 minus 140 into 166.47 minus 280 by 2, the whole squared. So IAL comes out to be 200 into, so this comes out to be 405.10 into 10 power 6 mm power 4. Similarly, I can calculate for steel also, which will come out to be 200 into 20 cubed by 12. This is self. 200 into 20 into this distance will be 280 plus 20 by 2 minus 166.47 the whole square. From the top, its center will be 280 plus 10, and I have to subtract this distance out. So that comes out to be 200 into 20 cubed by 12 plus 200 into 20 into 280 plus 20 by 2 minus 166.47 the whole square. This comes out to be 61. For steel, it is 61.17 into 10 power 6 mm power 4. We are able to see, we are able to note one thing is that even though this is a very thin plate, this has been placed sufficiently far away from the neutral axis such that its moment of inertia is a sizable fraction of the moment of inertia of the steel, the aluminum section. So that is the advantage of placing the material far away from the neutral axis. So let us calculate the curvature here. So the curvature comes out to be, by substitution, the moment is 50. So 1 by r, which is represented by kappa, is 50 into 10 power 6 by E is 70 E3 into this quantity plus 210 E3 into this quantity. We have this here. So this gives us the curvature. Curvature is represented by kappa, which is 1 by r or rho, however you want to see it. So 70 E3 into 405.1 E6 plus 210 E3 into 61.17 E6 into 50 E6. So this comes out to be 1 by 824054, or the radius of curvature is essentially 824.05 meters. Just to get a physical appreciation, we have a beam that is bending like this, and if I were to sketch its radius to the center of the curvature, it is nearly a kilometer long, which means the curvature is extremely flat. So that is what this means. So which makes sense that our deformations are extremely small, but so the radius of curvature comes out to be nearly a kilometer. Very well. So now that we have got the radius of curvature, it is just a matter of applying our flexure formula in order for us to arrive at the stresses. So let me take a copy of this. So using curvature, let me remove this. Using curvature, if I were to take this here, so this becomes my stress. Using my flexure formula, this is clear. So this is stress. I know the material, I know the radius of curvature, and I know I have to substitute y appropriately. So for this section, with the neutral axis over here, I can see that this distance is greater than this distance to the interface, which means that aluminium section will experience a greater stress over here than over here, because the stress is a linear function of y. And if y is more, stress will be more. Since the question asks the maximum bending stress in aluminium, in this specific problem, it so happens that the top point is actually undergoing the maximum stress rather than the aluminum bottom, that is the interface. So this has to be looked at from a holistic point of view, from question to question, and one is expected to assess this distance as to which will give the maximum stress and report the values appropriately as asked in the question. So for this case, essentially y that I need to substitute for aluminium will be yt, and for steel this will be the distance, which is nothing but minus 300 minus Yt as we have seen. So let us go ahead and substitute that. So for aluminium, Y is Yt for sigma max. So therefore, sigma x in aluminium maximum is nothing but minus E of aluminium. Let me write it as a symbol first. So this is minus EAL by R into Y max, which is nothing but minus 70 E3 by the radius was 824054. So 824054 into Y max is 166.47. So therefore, this quantity comes out to be 824054 into 47 into 70 E3. So this comes out to be minus 14.14 MPa. So this is the stress in aluminium. Similarly, for steel, Y max will be minus of 300 minus 166.47. Since steel is only on one side, there is no question about which value to substitute. It was only in the case of aluminium that there was there was some additional thought process needed. So this is minus 133.53 mm. So therefore, if I were to take the same thing for steel, this will be Y of steel, which is nothing but minus of 210 E3 divided by the same radius of curvature, which was 824054 into minus 133.53. So therefore, this quantity comes out to be minus 210 E3 into minus 133.53 divided by 824054. So this comes out to be plus 34.03 MPa, which is tensile, as we can see. And the stress in aluminium is compressive because it is on the opposite fiber. So which makes sense here. I'm sorry, just a minute. Very well. So these are the stress values from our curvature method. So these are the values from our curvature method. Now we will have to see if these match when we approach the same problem. We saw that in order to arrive at these values, we had to go through a circuitous process of integrating and finding the neutral axis first, followed by finding the moment of inertia, curvature, and from curvature we basically evaluated. Once we got the curvature, we basically evaluated the strain and multiplied it by the Young's modulus in order to arrive at the stress. So we took a circuitous process to solve this composite beam problem. Now let us see how this is to be addressed using the transform section method, which we will see is much easier. Although the rudiment still remains the same, this is transform section method is much more attractive in that it is easier. It doesn't involve many integrations. So which is what we will see next. So this is basically we have solved the question using the curvature method. Now I will quickly solve this using the transform section method. So what I'll do, I'll just let me take this. We will see that it is very similar in nature, except for some shortcuts we can take. So let me add a page here. Yeah, so using using the transform section method. So let us convert, or let us transform steel in terms of aluminum. So when we do that, basically whatever the width of steel is there, we just multiply it by the modular ratio. Why we multiply? If someone is interested, they can revisit this. Where did it go? Yeah, they can basically revisit this equation where we will see that the area here there would have been a B. So B into M. So this quantity we club it together and take it to be a homogeneous section. That is what we do. So it is coming from that. It is not that there is something special about the width, that we scale only the width. It is just that when this B comes here, when we take out the B, this MB becomes one unit. So we just take B as MB and take the entire section to be homogeneous in one of the materials. So that is the concept behind this. So if we were to do that, what I will have is, I will have a rectangle like that, and I will have a section like this, which is nearly 3 times the width. And the entire thing is now aluminum, where this is 200, this is 280, this is still 20, but this distance, this width is nothing but m times 200. M is 3, so this makes it 600. Once we have transformed everything to aluminum, I can simply apply my flexure formula because the entire section is homogeneous. Now the neutral axis of this will be the centroid of this cross section, and I have to take the moment of inertia about the centroid of this cross section and appropriately calculate the stresses. So I'll quickly do that. Granted, if there are any mismatch in the numbers, I encourage the viewers to check once again. I suppose there won't be, but in case there are, please bear with me. Okay, so let this be the centroid of cross section. Let this be Z, and let this distance be YT again. So how do I calculate YT? I just need to take the moment of the entire area about 1, and I have to equate it to 0. So YT can be calculated as sigma A Y about the top divided by sigma A, as we generally do for the case of any homogeneous section. So this will be 200 into 280 into 280 by 2, plus this is 600 into 20, 600 into 20 into 280 plus 10, or I should write 20 by 2 for clarity, divided by the entire area, which is 200 into 280 plus 600 into 20. So YT comes out to be into 280 into 280 by 2 plus 600 into 20, 280 plus 10 divided by, which comes out to be 166.47, which is identical to what we got with all the integration and so on. So I suppose you are able to see that this makes life much easier. So we have located this. Now quickly we have to calculate moment of inertia about this point. This distance we have got. So moment of inertia about that. I'll just bring the section here again once for clarity. So the moment of inertia is 200. I'm breaking this down into two rectangles and adding them up. So we will see that moment of inertia will be similarly calculated. 200 into 280 cubed by 12 plus 200 into 280 into 166.47 minus 280 by 2 the whole squared plus 600 into 20 cubed by 12 plus 600 into 20 into this distance will be 280 plus 20 by 2 minus 166.47 squared. What we will see if we compare this to what we did earlier was only this width remains unchanged. There we had calculated for aluminium separately, for steel separately. But when we calculated for steel, this was 200. Now we have homogenized the section, so to speak, and we have taken this to be 600 when we are adding up together as one unit. So IZZ comes out to be 280 cube, 200 into 280 cube by 12 plus squared plus 600 into 20 plus 600 into 20 into 280 plus 10 minus 166.47 the whole squared. So this comes out to be 588.619 into 10 power 6 mm power 4. I hope I have not made any calculation errors, but I encourage you to check it anyway. So now we have IZZ, we have our flexure formula. It is just a matter of finding out what the stresses are. So let us do that quickly. So I know if this goes here, I remove this. Minus comes here. This is my bending stress. So for the top fiber, I have Y is YT, which is plus 166.47 mm. For the interface between steel and uh, between steel and aluminum, for the interface, Y is minus of 280 minus YT, which was coming out to be minus of 280 minus 166.47. This is minus 113.53 mm. And for the bottom fiber, Y is nothing but minus of 300 minus YT, which is minus 133. Yeah, naturally, only 20 will get added here. So we just need to substitute that for Y and we will get stresses at three places. So at the top fiber, MB, I'm sorry, at the top fiber, stress is minus MB is 50 E6 into Y is 166.47 divided by I, which is this quantity. So I hope it will add up and come out to be the same. In any case, it should come out to be the same if all the calculations are right. So this is minus 50 E6 into 166.47 divided by 588.619 E6, which comes out to be minus 113.53 mm. 53 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 mm minus 14.14 MPa. Similarly, for steel, if we were to see for the bottom fiber, so for the bottom fiber, I just need to replace this value with this. So I'll just take this from here, plug it here. So this is equal to, so this will be minus 50 E6 into minus 133.53 divided by 588.619 E6. So this will come out to be 11.34 MPa. Now mind you, this stress, this is the tensile stress. Stress in transformed steel. Meaning we have actually widened the area. So the stress, it is this portion, this entire portion is taking that amount of stress. But in reality, steel is confined to this width only. So in order for us to convert from the transformed stress to the actual stress in steel, so therefore actual stress in steel would be equal to m times our sigma steel in transform, which is nothing but our 210 by 70, which is 3 into 11.34. So therefore sigma max in steel in the x direction is nothing but 3 times of this, which is 34.03 MPa. So this we get as 34.03 MPa. And for our for aluminium, this was coming out to be, so sigma x aluminium max comes out to be minus 14.14 MPa. So these are the answers we have got from our transformed section method, but mechanics remains the same. So the problem answer should be independent of the method that has been chosen. So if we were to verify these with our answers here, which we got from the curvature method, we are able to see that these are identical. So it is minus 14 and plus 34 in steel, which is what we are getting here as well. Only the saving grace is that in the transformed section method, we did not have to do much of integration and we did not take a circuitous process, except for the fact that at the end, we should always remember that we are the material which we have transformed into something else, we will be getting the stresses using this method only in the transformed material. So in order to get the actual stress, we will invariably have to multiply it by the modular ratio, which is the ratio of the Young's moduli. So I suppose now we are confident in approaching the problem of composite beams from curvature method as well as transformed section method, and we have been able to see that we are getting identical answers. So are there any questions at this point? Because I've been yapping for about 45 minutes straight. So if there are any questions, I would be happy to take them now. Is it clear what we discussed, or is it, did I? Okay. All right. Thank you. Okay. So, yeah.
Excuse me, sir. Could you explain the question number one, sir? I was late. I joined late.
Yeah. Yeah. Okay. 1 minute. Question number one. This one? The assignment question, you mean? Or this one?
Yes, sir. Yeah,
Why
this
this
is
is
sir.
zero? This one, is it? Okay. So actually, what this question is asking is, for a 3-point bend beam, which we are able to see here, that a beam is subjected to a point load at some point. The top and bottommost fibers at a distance of L by 3. So from the support, I have taken a section, a cut section, at a distance of L by 3, where L is the length of the member. At this section, at the top and bottommost fiber, they are asking what is the shear stress. Even without our knowledge of bending, if we were to just visit our free surface lecture, let me take the top point here and let me blow it up like this. I have just blown up the top point at L by 3 into this stress element. I know that at that element, I have a compressive stress because of bending. But the top surface actually has no stress, no applied load. It is only at this point we have a concentrated load applied. If I had a UDL applied like this, then naturally at the top I would be having some compression like this. It would no longer be a free surface. But the present question is asking what happens in a 3-point bend beam at that point. We are able to see this is totally free of any traction, right? So this is a free surface, which means normal stress as well as shear stress is zero there. Now, if I had shear stress existing like this, I will have shear stress exist like this, and so on, by equality of cross shears. But since that is not coming, I don't have shear stress in the picture. So at the top point, there is only one normal stress that is acting by virtue of bending. Same goes for the bottom point also. At the bottom point, only thing is this will be tensile, except there will be no shear there also. There at the bottom, this will be the free surface instead of the top point. So at the free surface, shear is zero. That is why shear stress is zero. Is it clear, sir?
Yes, sir.
If
Thank you so much.
okay. Thank you. Thank you very much. Okay, so I suppose we've run out of time. I think I delved a lot into this composite beam question, but rest assured that I will post this answer by solving it using both methods so that it is consistent for the viewers to see. There is this question where we have to populate the stress tensor. I think it is best that I will post a detailed explanation in this sheet itself so that it is at your disposal to see it whenever you want. Or in case you want me to explain this, I can do that also. I'll take a call based on your decision because we've run out of time. So if you want me to explain this, I can. Otherwise, we'll call it a day and I can perhaps post the solution of this question when I post this sheet. Please let me know. Explain. Okay, I'll explain then. So I'll just briefly explain and the detailed solution I will post when I post this sheet. So we have a simply supported beam with a central load which has 13 kilonewton applied. And we have been told that there is a rectangular cross section. So when we cut it here, what we see is a rectangle like this, where this is the y axis, this is the z axis, and x is pointing out of the plane of the paper. The planar stress component in the xy bending plane along the y direction has 4 points. So what we have done, this actually bends along this plane. I hope you are able to see. This beam, if we cut it in the plane of the paper at the center, we will get this plane. So that is the bending plane. At that bending plane, they have taken 4 points. Now, at each and every point, they have populated the stress tensor in one way. So what is important to understand is at point 1, the stress tensor ABCD, if we write it as an index notation, it will actually be sigma xx, tau xy, xy, and sigma yy. In fact, this will hold for any point. So what they are saying is, at these 4 points, I have taken the stress tensor represented in the xy coordinate system in that plane. So at z equal to 0, my stress tensor will look something like this at P1. At P2, these will have some different values, but nonetheless, the structure remains the same. And what we have been asked is to populate these stress tensors. So let us quickly do that, in fact. For point 1, what is it that we know? We know that it is at the top fiber. So shear cannot exist because it is a free surface. So B. So at point, in fact, they have named it in such a way that B only pertains to P point 1. Others are K, E, and H. So therefore, by virtue of the top surface being free, traction free, what do we know from there? My tau xy will be 0 and sigma yy will be 0. Because at this point, if I draw the stress element, I will have compressive stress like this and nothing else, as we discussed in the first question, which Mr. Praveen just asked. So in such a case, B and C are categorically 0. A, we don't know yet. A, we have to find out. So let us leave A for a while. Presently, I'll just populate which we know. B is 0 and C is 0. Are there any questions about this? Why B is 0 and C is 0? It is clear because it's a free surface, shear and the normal to that plane is 0. A does have a value. We will come to that. At point P2, which is at the neutral axis, and we are doing an engineering analysis here. So at the neutral axis, my normal stress is going to be 0. Why? Because the variation is going to be like that of sigma x. So at this point, I can see that it is subjected to no normal stress. So D is going to be 0 and F and I, sigma y is anyway going to be 0 throughout the section. So what I know from here is at the neutral axis, normal stress sigma x is going to be 0. And therefore, D is 0. And in fact, I should also qualify this y, that is. So tau xy is 0 and sigma yy is 0. Therefore, B, C and D are all 0. We have deduced this much. What else do we know? We know that sigma y doesn't exist in this problem. Sigma y may have existed on the top face if this was subjected to some UDL, but that is also not the case. This is a 3-point bend beam. So naturally, C, L, F, and I. C, L, F, I are 0 because except the loading points. Why I say points? Because the supports are also sort of loading points. So that is why I'm saying plural. So except for these, at other places, C, what else were the index? L, F, I. Since sigma yy is 0. So C 0, L, F, I. F is 0. Okay, others, actually all the indices are not asked, but I suppose you get the idea. So let us go back to what we don't know. So I'll just, in fact, I will circles the one that are pending so that we can address them one at a time. So A, we don't know. J and K, we are yet to calculate. D, we are yet to calculate. G, we are yet to calculate. Rest all components go to 0. I think that is clear. So at section AA, what is the shear force that is acting?
for this beam, if I draw the shear force diagram, it will be like this. And what is this height? It will be nothing but
13.5 by 2.
because the reaction is, it's a symmetric problem. So this is 13.5 by 2, right? So this is 6.25. So this is 6.25 kilonewton. Positive. I hope you are able to appreciate that because we are taking at this, according to this sign convention, I am taking. What is the bending moment at this section? The reaction is 6.25. This distance is half a meter. There is nothing else. So if I were to draw the section like this, my bending moment will come out to be into half, right? So it is 3.375 and this is also positive kilonewton meter.
Is there any are there any doubts about how we got shear force and bending moment at that section? I think that should be pretty clear.
Rest is only application of our
Shear formula and
flexure formula. So let us do that. So for this problem, we have deduced at section AA the shear force is this much. Therefore, shear stress tau xy is, for a rectangular section, we already derived the quantities. So I'll just take it from there. In one of the questions, we have done that. I'll just quickly go through. Yeah. So I already know my tau xy to be this for a case of rectangle. Now, in this case, what is it that I don't know? I know all the quantities. V I know. B and H are given in the question 150 and 300. V I have. Now it is just a matter of substituting for Y. So for obtaining K, what will be my Y? See, we are cutting a section at this point and this is the area we need to take. So Y is essentially this distance, which is given to be 70. So for obtaining tau xy at point P4, Y will be 70 mm. For obtaining that as the neutral axis, actually E also we don't know yet. I should have circled that.
E also we don't know. E is basically the maximum shear stress.
We know what is the shear force here. We know the area.
We can calculate the average, and by virtue of this being a rectangle, we know the actual maximum shear stress will be 1.5 times of that.
But I encourage the viewers to also plug the value of Y equal to 0. So for E, Y will be equal to 0. H we know,
B we know to be 0. So shear stress is taken care.
Now what do we want? Bending stress. I know this being a neutral axis, D is actually known. D is known to be 0. Now let us calculate the bending stress also. Into Y. I know the bending moment at that section.
I know IZZ for the rectangle, which is BH cube by 12.
BD cube by 12. Y. For calculating A, Y will be H by 2. H is 300, so this will be 150. For the next point, it will be again 75. For J, it will be 75. 70, sorry. For J, Y is 70 mm, and this is plus. What else is pending? At the neutral axis, we know there is no sigma x. And at point 3, G, it will be minus. For G, Y will be minus h by 2 because it is in the opposite direction. So this will be minus 150 mm. So it is just a matter of plugging into this formula and you will be able to populate the stress tensors. Is it clear, madam? Any questions on this? Anything? Okay. So, all right. So when I post the sheet, perhaps I will plug the things and ensure that the composite beam problem is also done completely. So in this session, we saw how to address problems of composite beams, shear formula essentially, and its applications. So I hope I have done some justice into explaining how this has come about and how these are to be applied to problems. So if there are any further questions, I'm happy to take them now. Otherwise, we can call it a day and we'll meet next week for discussions on week 10, next Friday, same time. If there are any questions, I welcome them. Please feel free to ask. Otherwise, we can wrap it up. Okay. Perhaps I think we can wind it up then. So I'll see you people next week. Thank you for attending. Thank you.